Hey everybody. So today is a pretty big lesson here. I'm gonna encourage you to at some points maybe take a pause. There's a pause halfway in between. There's a lot to digest here. Obviously we'll talk about many of these things in class. You might want to have, I have a series flow chart. You might want to have that handy to look at because what we're about to do is to look at different ways of testing whether or not series converge or not. Sometimes we can find some intervals of convergence, but one thing to keep in mind, and we're going to be kind of going back and forth here, is that we're talking about infinite series of numbers. So if you look at a sequence of numbers that are added up as a series, whether or not they converge to a certain sum or not is one way to think about what we're going to be doing. And the other thing is to also think about our power series. There's infinitely long polynomials, whether or not they converge to looking like another graph. We might not know what that graph looks like, but we'll be able to maybe know what it looks like on a certain interval of convergence. So keep in mind that we're talking about these infinitely long sums of numbers and infinitely long polynomials as well as we go back and forth. There's a couple big main topics here that we're going to make sure that we get onto our flashcards. If you're not doing it during the video here, we'll definitely do that in class. So these are some of the things that we're going to talk about here. The nth term test for divergence, a ratio test, an interval convergence, which we've discussed before in terms of geometric series, a direct comparison test, and telescoping series. All on individually, they're all pretty easy things, but we're going to try to hit a lot of things here today. So let's go. So let's do some basic algebra review here. So this is the first time we saw this notation was our interval of convergence for geometric series. Let's just make sure that we understand that this notation is the same as the interval from -1 to 1, non-inclusive, when we take the absolute value of x is less than 1. Or if I have an expression like this, so we can rewrite this like -1 is less than x minus 2, which is less than 1. And then I want to separate it out into two separate inequalities. So the inequality x minus 2 is less than 1, solve for that. The inequality -1 is less than x minus 2, solve that. And if you solve both of those, you get the interval from 1 to 3. I'm just looking at this as notation. This is going to come back a little bit later. Another situation, it could look something like this, which obviously would be this. And I hope you know that eventually that would simplify to this. All right, there will be probably times in this video where you're going to want to pause me and or rewind me and listen to what I had to say again, or to write something down on the slide. Please, please, please do that. All right, so this idea of convergence. The series that we're most interested in are the series that do converge. We already know some power series and what they converge to. Think about our sine of x, e to the x, cosine of x, ln of x plus 1. All those series that we now know, we know that they converge, and they converge to those given equations, those functions, along certain intervals of convergence. So we're going to be interested in other series to see if they converge as well. So again, we're going to see, does this series converge? And if so, for what values does it converge? Along what interval of convergence? Now, again, we can think of this two ways. We've been mostly thinking about it graphically, meaning that my power series, my infinitely long Taylor or Maclaurin polynomial series, whether or not they converge along a certain interval means that their graphs would be pretty close to each other and could be used for an approximation. But also remember that interval of convergence means that any of those values of x within that interval of convergence, you could substitute that into the polynomial, therefore getting now a series of numbers, and that series of numbers would converge. What it converges to, I might not know, but it would converge. So keep that in mind. All right, one of the fundamentals, first thing that has to be true for a series to converge is that the terms have to approach 0. So be thinking about like a series of numbers. Even for it to possibly converge, my numbers would have to be getting smaller and smaller and smaller in my series, like a half, a third, a fourth, a fifth, a sixth. Those numbers are getting smaller and smaller and smaller. So doesn't guarantee that it converges, but at least opens the possibility. If I had numbers like 1 plus 2 plus 3 plus 4 plus 5, well, obviously those numbers are getting bigger. Therefore, it's definitely going to diverge. So the sum of a sub nth term, it'll diverge if the limit of the nth term as n approaches infinity, if that nth term approaches infinity, or doesn't go to 0, it doesn't necessarily have to go to infinity. It just has to go to 0. So if the terms don't head towards 0, you cannot have convergence. Now, just because they don't head to 0 doesn't mean that it's going to diverge. Let me see, did I say that correct? So if the numbers don't head to 0, then the series definitely diverges. If the numbers do head towards 0, then there is a possibility that it converges, but you're not guaranteed. Let me show you. Yeah, so this is only proving divergence. You cannot use it to prove convergence. And it's the only test that we're going to see that explicitly proves divergence and not convergence. So here's a little example. So here's a power series. So I'm going to examine, so for what values of x do we have going on here, and to see whether or not this series converges, what happens to the numbers in this series. So if I pick an x value that's bigger than 1, I'm hoping you would see that, okay, this is a geometric term right here. So if I pick numbers like 2, 3, 4, 5, if I put 2, 3, 4, 5 in and then let n go to infinity, well, clearly those numbers are going to get bigger and bigger and bigger. So that's definitely going to diverge. But what about numbers between 0 and 1? Well, if I pick numbers between 0 and 1, that's going to create these fraction terms. But then those fractional terms are still going to be multiplied by n factorial. This in and of itself is not a geometric series. It has a little geometric term, but the whole series is not geometric. So if I examine that a little bit more, if I let these be fractions, I can rewrite this expression like this. And now I'm just kind of looking to see, well, eventually these fractions aren't going to grow as fast as this n factorial as n approaches infinity. So the numerator is still going to be growing faster. So therefore, this is going to head towards infinity. So therefore, that's not going to 0 either. So therefore, we can say that this series diverges. I've kind of looked at values bigger than 1, positive and negatives, and all the values between -1 and 1, positives and negatives. And all of those seem to get larger and larger and larger. So this series diverges, except for when x equals 0. If I let x equals 0, well, then all the terms in that series are going to be 0 plus 0 plus 0 plus 0 plus 0. So therefore, it's going to converge to 0. So there we go. That's a little bit of a complicated example, but we'll see easier ones a little bit later. And yes, you would want to make sure that you have this down. If you have some note cards, nth term test for divergence, you could have that on the one side and then the rule on the back. All right, so there's 3 possibilities for power series convergence. All right, so let's look at those. So a series can converge over some finite interval or some interval of convergence. Just like our geometric series, just like our series of, I think it was ln of x, and the series that have bounded intervals of convergence. Is one type of a series convergence. We will determine later whether or not it converges at the endpoints. We're going to use a ratio test usually to find an interval of convergence, but we'll learn later on how to test the endpoints. All right, so we've seen that already with geometric series. We also have seen where we have open intervals come to convergence, where they converge over an infinite interval, and those would be things series like the sine of x or cosine of x. But the more terms that you add, the bigger the radius of convergence is, and it just keeps getting wider and wider and wider. And then the last one is that it converges just at a single point and diverges everywhere else. For example, so therefore it has a radius of convergence of 0. So just happening in 1. This is what happened in that last example. It diverged for all other values except for just at x equals 0. And so again, that r is called the radius of convergence. Sometimes it's infinite, Sometimes it's some particular value, like in geometric series, a basic geometric series goes from -1 to 1, so a radius of 1. And then sometimes we have a radius that's 0 if it's just a single point of convergence. So let's take a look at an example of what we'll have to do here. So I want to find the center, the interval, and the radius of convergence for this series. Now I could write all these terms out. I'd have my first term would be 1 plus x plus 4 plus x plus 4 squared plus x plus 4 cubed, and so on and so forth. But I want to know what is the interval of convergence to whatever function that this is representing. At this point, I don't know what this, if I wrote out all these polynomial terms, I don't know what function that this is representing or helping us approximate. But I will be able to tell on what interval it will be a good approximation. So this is a geometric series. It's easy to tell because it's just a single term to the nth power. And we know that has an interval of convergence, first of all, of 1, typically. But in this case, my center is going to be at -4. So x equals -4. And let me come in here with a pen. So what I can do is I can say, okay, normal intervals of convergence, I know that R has to be between 1 and -1. So in this case, x plus 4, that's my R value. That's what I keep multiplying by every time. So I'm going to say x plus 4 is in between 1 and -1. And then so let's do what we did earlier. I can simplify that. Look at the 1 inequality. And that looks like that it's going to be x is less than -3 if I subtract 4 over to there. And if I subtract 4 over to the other side, I get -5. So here's my interval of convergence, which means I have a center right there at -4. And I just calculated my interval of convergence there. And so if my center's at -4, and then I'm going to -3 and -5, I therefore have a radius of convergence that is just 1. So again, I don't know what this converges to, but I know it's going to converge between -5 and -3. It's going to represent some other function for me to make approximations. All right, how about another one here? So once again, it is geometric. I can see this repeated term being to the nth power. So again, if you would like to, you could say x plus 2. That's my R value, not including that 2. That R value is between -1 and 1. And then if I simplify that, you can see I get my interval of convergence. That's usually the thing we figure out first. We can clearly see the center is at -2. And frankly, you could have seen that at the very beginning. This is a polynomial shifted to the left too. And then therefore I have a radius of convergence that is just 1. So from -2 to -1 and -2 to -3. Pretty easy. That's why geometric series are really our best friends, because we know a lot about them. Now, I will say, now that I've been saying this the last 2 slides, saying that we don't know what this converges to, well, we actually do, because these are geometric series. I could actually set a over 1 minus r and solve actually what this series is converging to on this particular interval. So in this case, we do know how to do this. All right. So another type of a test is a direct comparison test. So now that we've memorized some of those known series, we can use them to our advantage when given some other series. All right, so first of all, this has to be for non-negative series. If you're looking at the flow chart, you'll see that the 2 series in question, a sub n and b sub n, both have to be greater than or equal to 0. We are only talking about positive series, non-negative series. So if every term of a series is less than a corresponding term of a converging series, both series converge. And this should sound familiar. So we talked about this in terms of numerical series, when we were just looking at series of numbers. If I had a series that converged, the red one converges, then if I have a series that each term is below the other corresponding term, well, then the series below has to also converge. So for example, if I'm going to compare something to like an e to the x series, if I know all of the terms in my series are going to be less than the terms in the e to the x series, e to the x series, I know what it converges to. That's that polynomial function that we know. Well, then the given one will also converge. Well, it also works for divergence as well. If every term in a series is greater than a corresponding term of a diverging series, both of the series diverge. So if I'm given a particular series, my red series, and that series I know diverges. If that series diverges, then any series whose corresponding terms are greater than that given series, the diverging series, well, then that one's going to diverge as well. So we were thinking of that kind of, I think, along the lines of improper integrals earlier, but the same concept applies here. So let's look at an example here. I want to prove that this series converges for all real values of x. All right, and there's going to be a couple different ways we could do this. The way we're going to do it here is with the direct comparison test. I noticed that it's got all these squared terms. There's going to be no negative terms. So I can maybe think about the direct comparison test. So let's just see if you agree with this inequality. So the one term on the left is obviously my given series term. And I invite you, if you want to, you could start with n equals 0, go and take this series, and you could start writing out all the polynomial terms and see what those polynomial terms look like. Let n equals 0, substitute in, n equals 1, substitute it in. Not necessary to do, but we could do that. Okay, so this is going to be less than this other series over here. Well, yeah, because that has a larger denominator, which creates a smaller fraction. Fine. Well, but what do we know about this series? If I'm going to do a direct comparison, I got to know if this series converges or not. So look real carefully. Do we know, does this look familiar? I got a term to the nth power over n factorial. Yeah, that looks like the e to the x series. But instead of x to the n, it's x squared to the n. So this is actually the series for e to the x squared. So now you can kind of start to see the reason why we wanted to memorize some of those other series. This series, I know it converges, and it converges to e to the x squared, which has an open interval of convergence, which we already know. So therefore, by the direct comparison series, if the series above converges, then the series bounded below is also going to converge as well. So here's a really good example of where we're going to be using those known series to do some comparisons. Yeah, was this a little sneaky? But we'll talk about how to maybe make some good guesses about what series to compare things to. So again, this only works if the terms are not negative, non-negative terms. All right, so something to kind of think about, this concept kind of comes up sometimes on the exam. We should be aware of at least the vocabulary here of absolute versus conditional convergence. All right, so if I go ahead and take the absolute value of all the terms in a series, so obviously we have some series that have negative terms, some terms that alternate positive, negative, positive, negative. But if I take the absolute value of all those terms in the series, and that converges, well, then we say that the original series it converges absolutely. Now, we don't mean like definitely converges. It means the actual mathematical term of absolute convergence, meaning that it's only converging over those positive numbers. So that is one type of convergence. If I take the absolute value of the series converges, then the actual series itself is also converges. So by you taking the absolute value and you've proven that converges, we can then therefore say that the series converges. It converges by absolute convergence. All right. That's what I just said. All right. So another situation then is if the series itself converges, and we've figured out a way either through a direct comparison or something else, but the absolute value of it diverges, then we say that the original series converges conditionally on certain conditions. So that is conditional convergence. And let me give you some examples of each of these. Pause if you need to. All right, so my three scenarios could be the series could converge absolutely, it can converge conditionally, or the series could diverge. So here's an example of absolute convergence. So this is a simple little geometric series, -1/2, that is within the interval of convergence. So the series itself definitely converges. So, and you could see if I were to write those terms out, it would be plus minus, plus minus, plus minus. But if then I make them all positive, take their absolute value, well, then that's just a geometric series with a common ratio of just +1/2. Well, both of those series converges either on its own or absolute convergence, just looking at all the positives. So that's considered absolute convergence. It definitely converges for both. However, it's going to converge to 2 different values. You'll find that we're going to be probably talking a lot that we don't care about what things converge to, just whether or not they converge or not. Second is conditional convergence. So in this case, this is an example of the harmonic series. So if I let n equals 1 all the way up to infinity, so my series would be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. So that's alternating back and forth. And that particular series actually converges. And we'll talk about later why that converges. But if I take all of those terms and make them positive, take their absolute value, that series diverges. And we have seen that one. That's the 1/2, the 1/3, the 4th, the 5th, plus the 6th, plus the 7th. That diverges. So this is an example of a conditional convergence, this harmonic series. So the alternating harmonic converges, but the actual harmonic series itself diverges. All right, and the last one in this case is a diverging series. Again, talking about series of numbers. If I just let n equals 1 up to infinity, well, then I just get this ping-ponging back and forth, 1, -1, 1, -1, 1, -1, which that I don't know converges to 0, so that diverges. And then if I just take its absolute value, which would just be 1 plus 1 plus 1 plus 1, obviously that goes to infinity, and that diverges too. So there's a diverging series. We'll talk about situations where we want to maybe name these. All right, so let's look at this series and see whether or not it converges or not. Definitely not geometric because of that n factorial in the denominator. Otherwise, the numerator term is a geometric term, but the whole series is not. So let's test for absolute convergence. So if I take its absolute value, obviously the sine function goes back and forth between 1 and -1. So I think I can set up this inequality. Just think about why that would be true. So that absolute value of sine of x, that has to be less than or equal to 1. Can't go a bit bigger than 1 because of the amplitude of the sine function. So we know that that's true. The question is, if I'm going to be comparing it to this, I must know something about this particular series. Well, Mr. Good, it doesn't look like anything we've ever dealt with before. But if you think about it, that single solitary little n factorial in the denominator, that's a giveaway that maybe I'm talking about e to the x. But how do I get that numerator to just be a 1? Now, if I let that numerator just be a 1, this is going to wind up then just converging to e to the 1, because if I let the numerator be 1, that means x would have to be 1. 1 to any power is going to give me 1. So therefore, this must be converging to e. So this 1 over n factorial is actually a way to calculate e, the summing of that up. So I know that this converges, and I actually know what this converges to. This converges to e. So therefore, I've got the lower series, the series that's below it, its absolute values converging. So therefore, the absolute value of that series converges, so we say that it converges absolutely. And if it converges absolutely, the absolute value of all of those, then we know that the series itself also converges. All right, and there's a lot to kind of digest at this point. If you need to take a pause right here and come on back. So we've talked about a little bit of intervals convergence, direct comparison, convergence, and we talked about absolute convergence and conditional convergence. All right, so let's keep moving on and talk about one of the most famous things and things that you're going to most definitely have to do in the exam. Well, you will have to do it on the exam, and it's a good likelihood you have to do it on the free response question. This is typically one they want to see you guys do, and it's called a ratio test. So geometric series, let me get my little cursor back here. All right, geometric series have ratios that are constant, but other ratios have series that are non-constant. Geometric series, we keep multiplying by the same term over and over and over again, but not all series have ratios that stay constant. Well, if the absolute value of the limit of the ratio between consecutive terms is less than 1, the series will converge. So what does that mean? So if I've got some kind of a series, I'm calling it T sub n instead of A sub n, don't let that throw you off. Well, my limit of the successive terms, these are the nth plus 1 term over the nth term, if the limit of that ratio turns out to be a certain value, we can tell whether or not it converges or diverges. Well, if that limit comes out less than 1, we know the series will converge. And if you think about it, that makes sense, because if you take one term divided by the term that came before, you're actually calculating the ratio. And if that ratio came out less than 1, that means those terms you'd be multiplying by would be getting smaller and smaller and smaller. Therefore, a good likelihood to converge. Well, the ratio test says it will. If that ratio turns out bigger than 1, you're obviously multiplying by something larger than 1, it's definitely going to diverge. The terms keep getting bigger and bigger and bigger. But if the limit comes out to be exactly 1, well, we don't know if it's going to converge or diverge, and we're going to have to come up with another test. So not only is the ratio test going to be good, you want to make sure that you're getting this down, that it's good for determining convergence, it's actually good for helping us determine intervals of convergence, which ultimately will have to be testing some endpoints. But let's take a look at an example of the ratio test in action. This is actually pretty easy. It's very algebraic. And again, a very common thing to see on a free response question. All right, so let's look at this particular example. So this is not exact, this could be something you would see on the exam, finding the interval of convergence for the ln of x. So let's start out with our series that we do know. We know the ln of 1 plus x, and there's the first couple terms of it. Well, if I replace the x with an x minus 1, so I would be putting x minus 1 in for x, and then 1 plus x minus 1 is just going to be x. So that means I replaced all those other terms with an x minus 1. So I'm just taking a known series and manipulating it. So here's ln of x. So replacing my series, my nth term for my ln of 1 plus x, that replacing with an x plus 1, or sorry, x minus 1, I get that expression. All right, so let's use the ratio test here. All right, so what the ratio test is doing, let me grab my pen here, is taking the nth plus 1th term divided by the nth term. And so this is the nth term right here. So that is the nth term. So that would be technically in the denominator. But you can see I already have some fractions here. So a lot of times what we're going to do with the ratio test is we're going to take it as the nth plus 1 term times the reciprocal of the nth term. That is still the same as dividing the nth plus 1 term divided by the nth term. So this is the way that we're going to usually do it to help us do some cancellations. So this right here, this second fraction, is the reciprocal of this given series. That's the a sub nth term, just now flipped upside down. And then this over here on the left is the nth plus 1. So all I'm going in is replacing all the n's in my expression with n plus 1. And I get that expression. So here's my nth plus 1 term, and here's the reciprocal of the nth term. All right, so we can see what we've got here. Let me clear this out. So now I want to see what the limit of this ratio is. So now I'm going to go through and I'm going to try to clean this up a little bit. Well, first of all, I'm dealing with absolute value. So these two terms are just creating positive, negatives. Well, they're all going to become positive, so get rid of those. So next, what I'd like to do is I'm a big fan of taking this particular term and separating it. And you'll see why in a second. So it's x minus 1 to the nth and x minus 1 to the first. Because you can probably see now that those two cancel out. So now I'm left with this expression. And what am I trying to find? The limit as n approaches infinity. So x is not involved in me calculating this limit. It's just the n's. So I let n approach infinity. Obviously, we've got a L'Hopital issue here, so I'm going to have to take the derivative once, and therefore I just get absolute value of x minus 1. Well, that doesn't tell me right now whether or not it converges or diverges. Remember a second ago, if that limit stayed less than 1, then it converged. So I'm now going to force this to be less than 1, so I can figure out when it converges. So if this looks familiar, this is the first thing we talked about at the beginning. So I'm going to break this apart and simplify it, add 1 to both sides of this inequality, or separate the inequalities into 2 inequalities. And so therefore, my interval of convergence is between 0 and 2 with a radius of convergence of 1. So therefore, I can say that this polynomial is going to converge to the ln of x on the interval from 0 to 2. If also then, if I pick any, so you can think about that graphically. Also, if I pick any number between 0 and 2 and substitute it in, it's going to substitute it into the polynomial. It is going to give me a polynomial that will ultimately sum up to whatever the ln of x is at that value. All right, so let's look at another example. So I want to find probably the interval of convergence. So in this case, first of all, it's not, this looks nothing like any of my known series. It's definitely not geometric. So I'm going to perform a ratio test on this. So let's just write a couple terms out just so you can kind of see what's happening here. Here's me just, and this is not necessary to do, just so you can see that this creates a power series. And I would like to know what it converges on what interval. So here's my nth plus 1 term. That's this series itself, but now with n plus 1s in for all the n's. Divided by the nth term, well, or times by the reciprocal of the nth term. It's the same thing as dividing, multiplying by its reciprocal. And now we want to clean this up and see what happens. All right. So first thing you'll see is there wasn't any negative terms. So I'm just splitting this particular term apart, and I'm splitting this particular term apart to make it a little bit easier for me to then do some canceling. These are just to the first powers. So separate those out, and yeah, bunches of things will start to cancel. Another set of things cancel. And then I get this expression. All right, so now that I have this expression, I want to see what is the limit as n approaches infinity. Let me come up here. All right, now, first thing I'm also then going to suggest is, since we're not touching the x term because the limit is in terms of n, maybe bring that out. Absolute value of x minus 5 comes out. And now this just becomes a simple little L'Hopital, which hopefully we see comes out to be a third. You don't have to actually write that out. So now this is what the limit is of the a plus nth term over the nth term. So I want to figure out when it converges. So I'm going to force that less than 1, because by the ratio test, that's when it converges. So once again, we can simplify this first. This is the first time I guess we've seen a constant out in front of coefficient. So multiply by 3, separate it out, do your separate intervals. And so there we go. I know that this has an interval of convergence from 2 to 8. And so if I see from 2 to 8, that's 6 is the actual range. So therefore it must have a radius of convergence of just 3. Sometimes asking for radiuses of convergence again. So that infinitely long polynomial converges to some other function that I don't know what it is, but it does between 2 and 8, meaning that between 2 and 8, I can use that polynomial function to approximate some other function here. All right, how about me let you try to set this up, pause me here quick, and at least set up the a plus nth term times the reciprocal of the nth term, and maybe kind of start to separate some terms out, and then we'll talk. Right, me just writing out a whole bunch of terms just so I can kind of see this has been simplified. So just so we have a sense of that's the polynomial function that I'm dealing with, trying to find its interval of convergence. All right, so here we go. So my a sub nth term, so all of the n's get replaced with an n plus 1. Sorry, a sub n plus 1, I should say. All my n's replaced with an n plus 1. And then again, this is my a sub nth term that I would be technically dividing by according to the ratio test, but I'm really multiplying by its reciprocal to make my algebra a little bit easier. All right, starting to separate things out. You know, you probably did the n plus 1, separated that out, but also n plus 1 factorial can be separated as well. So that's going to be separated by n plus 1 times n factorial. So if you think of it, the n plus 1 term, if I just separate that term out, then all the terms that came before it, all n terms down to 1, then that just remains as a factorial. So n plus 1 factorial is equal to n plus 1 times n factorial. That's a nice thing for us to know in terms of simplifying, and we'll probably see that pretty often. And now let's go start canceling. N factorials go away, x minus 3 to the nths go away. And so once again, I'm going to bring that absolute value of x minus 3 out. And I got the rest of this to kind of clean up. Well, as n approaches infinity, this is just going to go to 1. And then, so therefore we can see that this is definitely going to go to infinity. It's definitely going to get, this term is going to definitely go to infinity. So therefore, heading off to infinity for all values, except for when x equals 3, because when x equals 3, that's going to create a 0 term, so all of the terms are going to be 0, so it would converge to 0. So therefore, this has a radius of convergence of 0. There is no interval convergence because that ratio turned out to be infinite. It's just said that right there. All right. So again, this had a radius of convergence of 0, but if the radius of convergence was infinite, then it converges for all the values in that series. All right, last thing, promise. Okay, this one's a fun one. Okay, sometimes this pops up on the AP exam. I haven't seen it a whole lot, but we should talk about it. It's a telescoping series. All right. So telescoping series are one of the few series, in addition to like a geometric series or a known series, where I know what the sum will be. So this is an example of a telescoping series. All right, so I have this particular series. Now, this is not geometric, so I don't see that nth power anywhere. But if I actually use partial fractions, you know, you can see I'm not doing any integration here. But if I use partial fractions, watch what's going to happen. So I do what I normally do. Now this is a little slightly different technique. Oh no, this is, yeah, no, this is what we usually do. Yeah, this is the different technique right here, separating these out. But in the end, you go through and solve, you should be getting that A is 1 and B is -1. So I don't have a doubt that you have any problems doing that. So that means now my sum can be rewritten like this. So my nth term can now be separated into 1 over n. Now you might want to write plus -1. I could do that. Over n plus 1. So that's what we would have gotten. So what we do in this case is that I actually start writing the terms out. So I'm going to start writing the terms out. Let n equals 1, substitute it in. Get those two terms and keep them separated. Don't combine them. Then I go to my next term when n equals 2. So then I put 2 in. There's a half, and then minus -1/3. And then I do the next. And I do that for a couple. And if you look really carefully, you'll start to see, oh, -1/2 and a half cancel. -1/3 and a third cancel. So if I just wanted the third partial sum, it would just be 1 minus 1/4. But if I think about what's going to happen here on out, all the rest of those terms are going to collapse. They're all going to cancel out. Think about it like when you extend a telescope or collapse it in. All the rest of the series is going to collapse and cancel out. So therefore, this series, in the end, if I let now n approach infinity, That second term, this is just going to go to 0. So I know that the sum of this series is 1. So this is an example where, and the giveaway of when I know that it's a telescoping series is when there's some kind of a situation where I can factor the denominator and use partial fractions, because I need those two terms so that those two terms can cancel out on each other. So we'll see examples of that in the future, but wanted you to see at least an example of another series in addition to the geometric series where I will know its sum. All right, guys. That is a lot for us to do. All right, so just make sure you're using your series flow chart. Please practice the problems I'm assigning. I'm not assigning a lot, but I'm assigning enough for you to see and practice with what we've been doing here over the next day or two. This nth term test for divergence, the direct comparison test, the ratio test are some of the most common tests on the exam, especially that ratio test. So we want to make sure we're practicing these techniques. So make sure you're hopping online and looking what I'm looking for you to do. And please ask questions, All right, guys, good luck.